We've seen before how the Bode approximation provides a useful way to approximate the amplitude response of networks if you know where the poles and the zeros are. Well, there is a form of the Bode approximation that can approximate the phase response of these networks as well. And in this video, I'd like to introduce it. As before, we'll go through the three types of zeros and poles in turn. Firstly, zeros at 0 Hz. Well, zeros at 0 Hz make a contribution to the overall frequency response. H of j omega equals j omega. And it multiplies with the contributions of the gain and all of the zeros and all of the poles. And we've seen this kind of thing before. Now, if you consider writing each of these terms in its polar form, I could write this as the magnitude of the frequency response times e to the j, the phase of the frequency response. I'll just write that as theta function of omega equals the magnitude of g times e to the power of j, the phase of g. J omega has a magnitude of omega and a phase of 90 degrees, or pi over 2, so that would be just omega times e to the j pi over 2. That's the term that's contributed by my 0 at 0 Hz. And then this 0 here would have a magnitude. I'll just write that as, I don't know, mz for now, the magnitude of this term here, and its phase would be e to the power of j times the arctangent of, well, the imaginary part divided by the real part. The imaginary part is omega over minus z, the real part is 1, that's just minus omega over z. The effect of the pole is just the magnitude of the pole. I'll just write it as that. It doesn't really matter for this discussion. The phase of this term here is e to the power of j times the arctangent of the imaginary component divided by the real component. In that case, this is a tan of minus omega over p. Now, if I just equate the phase of the left-hand side of this equation with the phase of the right-hand side of this equation, I would get omega theta, that's the phase response, is omega g plus pi over 2 plus the arctangent of minus omega over z minus the arctangent of minus omega over p. And I've used the fact here that e to the power of x times e to the power of y is just e to the power of x plus y. And e to the power of x divided by e to the power of y is e to the power of x minus y, which is why there's a minus sign here. This term here is on the denominator. It divides the rest of the terms. So, the effect of my 0 at 0 Hz is to introduce a phase change of pi over 2. And if I had more than one 0 at 0 Hz, each one of those zeros would introduce phase change of pi over 2. This is not a function of frequency, it's pi over 2 at all frequencies. Now, how about the zeros not at 0 Hz? That's these ones here. Noting that arctangent is an odd function, I could write this as minus a tan of omega over z, or on the slide I've been working in hertz, so I've written as f. So slightly confusing. This z is in radians per second, this z is in hertz. Sorry about that. Anyway, if you plot this, you get this type of graph. Now, the Bode approximation for phase says that when you have a graph like this, you can approximate the phase response by saying that the phase has a constant value of 0, i.e. the 0, in this case, has no effect up to a frequency of 1/10 of the break frequency of the zero. This graph has been drawn for a zero at 1. And similarly, for frequencies greater than 10 times the frequency of the break frequency of the zero, the effect of the zero has its full effect, so that's going to be a complete 90 degrees. In between the two, you just draw a straight line. So that's the Bode approximation to phase for a zero at a frequency of 1. And you can see from the graph, it's not too bad an approximation. For a pole, a very similar thing happens, only for a pole, at frequencies below 1/10 of the break frequency of the pole, you assume that there is no effect on the phase response from the pole, and at frequencies greater than 10 times the break frequency of the pole, you assume that the pole has its full effect and introduces a phase change of minus 90 degrees. In between the two, 1/10 of the break frequency to 10 times the break frequency, you just draw a straight line. You then just add up the effects of all of these poles and zeros. I'll just do a simple example of this. Supposing we have this circuit here. We've seen before that the frequency response of this circuit, h of omega, is j omega RC over 1 plus j omega RC. It has a single zero at 0 Hertz, and it has a single pole at minus 1 over RC radians per second. So I've got a zero at 0 Hertz and a pole at minus 1 over RC radians per second, because that's the value of j omega when the denominator is 0, which means it will be at minus 1 over 2 pi RC Hertz. So the break frequency of the pole, I'll call it Fp, is the modulus of the pole, that's 1 over 2 pi RC in Hertz, and the break frequency of the zero, that's just 0. Right, the effect of a zero at 0 Hertz on the phase change of a signal going through this network, if this is the input here, and this is the output here, is to introduce a frequency independent offset of pi over 2, or if I'm working in degrees, 90 degrees. So that would be the contribution of the zero. The contribution of the pole, if we're using the Bode approximation, is we assume it has no effect at all up to 1/10 of the break frequency of the pole, which means up to 1 over 20 pi RC. The pole has no effect on the phase at all. And above 10 times the break frequency of the pole, which would be in this case 5 over pi RC, the effect of the pole is to introduce a phase change of minus 90 degrees. In this intermediate region, between 1/10 and 10 times the break frequency of the pole, the Bode approximation assumes that the phase changes linearly from one value to the other. So this is the effect of the pole on the phase. To produce the Bode approximation for the phase change of this whole network, we just have to add up these two contributions. That means we'd be starting at there, 90 plus 0 is 90, until we get to this point here. Then the pole would start to decrease it until we got to this point here, when the zero is introducing a plus 90, the pole is introducing a minus 90, add them up and you get nothing. So this would be the Bode approximation of the phase of this network. That's all I'm going to say about poles and zeros in general for now. In future videos, we're going to look at some specific examples. primarily of first order and second order circuits. That's circuits with either one pole or two poles in them.